Hello everyone, my name is Madison Pratt and I am a senior computational mathematics major with a minor in biology at Penn State. Today I'm going to tell you about my research on further understanding between host infectious disease dynamics through stability analysis of a delayed differential system of equations that we created to describe the amount of susceptible, infected, and recovered individuals throughout the course of an epidemic. The overarching title of my research is Stability Analysis of SIRS-like Delayed Renewal Equations. The motivation of this research comes from historical data from the pre-vaccination era for measles. Measles, among other diseases, has been known to show significant fluctuations in infection prevalence throughout time. As seen in Figure 1, the peaks and troughs of infection do not occur on a periodic basis. To understand the periodicity of infection, we developed a delayed renewal model to determine the stability of an infection within a population. The prevalence of infection within a population strongly depends on the maintenance of a chain of transmission. This means that there must be a continual influx of susceptible individuals within a population for the pathogen to have hosts to infect continually. Figure 2 is a simulation of an epidemic using our delayed renewal model. The curves show the susceptible individuals throughout time. Depending on the parameter values that we give our model, some of these curves dampen to stable levels, while others that have different parameter values may converge to a periodic solution. In order to understand more about how we will determine which parameter values make our model periodic or stable, it is important to perform similar analysis on previous models used in describing infection prevalence. The susceptible, infected, recovered, susceptible is a model comprised of three ordinary differential equations that describe the amount of susceptible, infected, and recovered individuals within a population throughout time, where individuals that recover from infection may become susceptible again after their immunity wears off. From this model, it was found that there are two outcomes for infection prevalence. The first outcome is disease-free state, where the infection is not strong enough to infect other individuals, and this results in a 100% susceptible population. Conversely, if an infection is strong enough, there will be a stable number of infected individuals throughout time. Figure 3 shows these two results. The axes on both graphs are susceptible versus infected individuals, showing that no matter how many people start out infected, the system will always converge upon one of these two equilibrium points, depending on the parameter values used. As stated previously, our model produces periodic infection prevalence as well as a steady infection prevalence. The reason our model differs from the SIRS model is that ours relies on a rate denoted JFT, which is the addition of new cases of disease throughout time. The strength of JFT is dependent on the average duration of infection, the average duration of recovery, the transmission rate of the disease, and the natural mortality rate within our model. Figure 4 shows a flow diagram of our model, where individuals leave the susceptible population at a rate of JFT and eventually leave the recovery class back into the susceptible pool at the rate of JFT for which they left the susceptible pool with. When the parameter values that make up JFT change, it creates different outcomes of infection prevalence within our model. Figure 5 is a graphical representation of stability analysis on the simplest version of our model. If we set the average duration of infection and recovery to 1 and the mortality rate to 0, the parameter controlling the addition of infection is the transmission rate, denoted beta. Figure 5 shows many curves inside of each other. Each of these curves is a mapping of the characteristic equation's real and imaginary part for a given value of beta. A system is known to converge to stability if all the real parts of the eigenvalues are negative. Figure 5 shows this because we plugged in all possible positive eigenvalues for the system, and none of them touched the origin, meaning that there are no solutions to the characteristic equation with positive real part. From this, we found the system will have a dampened infection prevalence to a stable level for transmission rates between 1 and 6.3. We have been performing similar analysis on more complicated versions of our model, where all of the parameter values are not constant, to determine what combination of parameter values result in a stable endemic state. I would like to thank my research advisor, Dr. Timothy Reluga, for helping me throughout this process, and below are some references you can check out to learn more. Thank you for your time. I hope you learned something new. That concludes my research poster presentation, and now I would like to take time to address the excellence, and literacy questions. The research process for me has taken about a full year, with being a full-time student at Penn State. And because this was my Schreier thesis topic, it was a lot longer than a 20-page paper. About a year ago, I was just starting my research and first began looking at a lot of models that were already used to describe infectious diseases, and finding out more about where they originated and how they are evolving. In the beginning, my search terms were much broader, like infectious disease mathematical models, or just looking for compartmental models. But as I began to get more technical with my research, so were my research topics that I would explore. So I started looking at more direct questions like chain of transmission and things that were more niche to my model that I was making. I was fortunate to have a lot of great researchers at Penn State who work in infectious disease dynamics, and many of my papers I cited came from the instructors I have had in class. I mainly utilized Penn State libraries to gain access to journal articles and books, and I spoke with someone from Penn State that helped me tailor my Google Scholar search engine to help me really find topics closer related to what I was looking for through common words and recently cited sources. Without the resources that Penn State provided me, I really would have struggled to gain access to all of the books and articles without having to pay money. Being able to get these sources for free really helped me learn a lot about this topic in such a short period of time, and as a student researcher, it is crucial to have as many resources as possible. I think a lot of people who don't have this kind of access use public libraries and read just what's available, and I wish that other people could have more access to these up-and-coming research topics, but unfortunately, I don't think they do. That's why it's also important to make connections with people who are knowledgeable about a subject. And if I didn't have Penn State, I would research who's working on research in my field and contact them directly in hopes that they can send me PDFs of relevant work for free. I have been fortunate enough to be accepted into Carnegie Mellon's computational biology program for this fall, where I hope to continue my research. I think I'm going to try and branch out to something less theoretical and more computational, because this is ultimately where my field is evolving to. Throughout my life and career path, I hope to be a lifelong researcher and to keep utilizing all sorts of resources to learn more about my field of study. I also hope to produce meaningful work in infectious disease dynamics that can save lives and lift the research community further to expedite the process in finding answers and helping others. I'm really thankful for all the opportunities that Penn State has poured into me, and I hope I can use all of those experiences as a launching pad as I become more advanced in my field. Thank you.